All right. Hello, everyone. If you remember from our last example, we just integrated with respect to y and then x and then y. And we found out that we got the same numbers. And what's really nice here in mathematics is that this is no coincidence. And actually, this is due to a famous theorem. And why don't we take this chance to write it out? So it is called Fubini's theorem. All right, so in order to do Fubini's theorem, you need to make sure that your function is continuous. And let's say it's continuous on the rectangle R, where R is that same rectangle that we described earlier. So it's the x's and y's such that x's range from A to B and the y's range from C to D. Okay, then Fubini's theorem says if we're trying to find this iterated integral, then we can either do it with respect to y first, or we can switch the limits of integration and do it with respect to x first. Alright, so it's really nice. I guess what I wanted to do was to explain some motivation as to why we have this theorem. And the other thing to keep in mind is that the actual proof you would see in an analysis class. So motivation. Let's see, I need a picture. Let's see if I can find it real easily. Copy. There we are. Now let's shrink it down just a little bit more. And there we go. Okay, so motivation. What we want to do is focus in on these pictures. So first of all, let's look at this integral. So from A to B, C to D. If we look at this inside integral, we see that x is constant, and it will give us the area under the curve where x is constant. Okay, and so we discussed earlier that we could write it as the integral from A to B of some function of A of x. We're calling that A. And so if you look over here in our picture, we have here x is constant. We're integrating underneath the integral. And this little sliver thing here is what we're calling A of x. And so notice now that our integral that we have, the smallest x value is A, so we're going to get this one back here. And then the biggest x value is B, so then we're going to get this one over here. And then we actually get all of the things in between there also. So it's like a nice sweeping motion. Okay, and we're just adding up those areas. And then versus if we look at adding up the other integral. So if we change the limits of integration, so first we go with respect to x. We see that here y is a constant, and we're still finding the area under the curve. But now y is constant, so we're going to get actually, so here it's kind of hard to see, but we have y is constant here. We're going to be integrating underneath our function, and so we get this area. So instead of having a of x, we're going to actually get a function that's changing with respect to y. So here we are. We get some other area, and it's with respect to y now. And so we also see that the smallest y value is c, so we would get this sliver, this area, and then it goes all the way till we get to d. And since we're integrating, it's just going to do a sweeping motion this way. Okay, to finish it up, you see that no matter which way we add these things up, we're going to get the same volume. And that is the motivation for Fubini's theorem. Okay, so the next one that we're going to do is we're just going to look at another example, and basically what's going to happen is we'll do it one way, and I want you to double check if you do it the other way that you get the same answer. So kind of verifying Fubini's theorem. Okay, so here we go. We want to evaluate this. I guess I'm running out of time for this one. So basically, I'll see you in the next video, and we'll start off here.